Welcome to the presentation of the work titled Model-Based Generation of Hardware-Software Architectures for Robotic Systems. Modern robots are complex systems which include heterogeneous sensors and actuators. Usually, they impose hard real-time constraints because failing to meet the deadlines could bring fatal consequences. Usually, these sort of systems are fitted with embedded computers which are not fully capable of parallel processing. FPGAs have been proven to be beneficial for robotic systems according to the literature due to the fact of their low energy consumptions and their concurrency capabilities. However, designing FPGA-based architectures is an arduous process. Architectures should facilitate the development of robotic systems, and they should provide helpful constraints on the design and implementations of the desired applications without being overly restrictive. A typical robotic system usually includes different types of components like CPUs, accelerators, and those that act as interfaces between the first two, called converters, which can be publishers or subscribers. The figure shows an example of our targeted architecture, which follows the zinc device model with a processing system and a programmable logic. Our research questions are how to generate all components for FPGA-based architectures for robotic systems from a holistic model and how that model should be defined. The description of the system should be compact, concise, but expressive enough, containing the necessary information to derive the system's components and their relations. The approach must be generic rather than application-specific, and it must exploit the benefits of FPGAs over software solutions without bringing any overhead. Three main challenges arise: how to obtain the explicit and derive the implicit information from a compact and meaningful system specification, and understand the specifications of interfaces for all components and their relations. Our first contribution is the comprehensive analysis of the system specification to derive the holistic model that includes all components to generate, their characteristics, interfaces, and how they all interact among each other. The second one is the generation of interfaces for accelerators based on middleware specifications to ease their integration, and the last one is a tailored scheduler for hybrid hardware-software architectures. Here we see how the system specification for the architecture shown before looks like. It is composed by three parts. The project name and the FPGA part are defined in the first one. From here, the FPGA family can be derived, which will dictate how to set certain configurations. The second one is where all the accelerators are defined by their type, either in HLS or VHDL, and this can be extended. Moreover, one component can be implemented in software with the intention to be accelerated. Then, hardware wrappers for the specified interface to robotic middlewares and type are generated. In case the type is specified without sources, the wrappers will also be generated to aid the developer with the integration of the new hardware component into the given middleware. Therefore, the middleware message and type must be defined. The last one concerns how all the components, accelerators, and interfaces interact among them. This is used to derive the necessary signals to interconnect all of them as specified. The workflow of the proposed toolchain is shown here. In the model analysis, the information to generate the different converters, wrappers for accelerators, and tailor scripts to deploy automatically the architecture is deduced only from the system specification. All required information that is not explicitly defined is derived by doing data type and data flow analysis of the messages, types, and connections of the components. The template engine along with templates are used to generate the intermediate artifacts. A template is a generic source code that resembles the expected artifacts. It is expanded with given specification from the template configuration accordingly to the needs, for example, names or bit widths. The templates are included in the tool. They are coded once and reused for any system specification. In this case, a logicless separate approach is used rather than program instructions, which simplifies the definition of templates for domain experts. Therefore, all the analysis and reasoning must happen within the tool. There are multiple templates according to the intermediate artifact to generate. This can be for HLS or VHDL sources, or tailor scripts as configurations for vendor-dependent tools to generate the expected components. New templates can be added to the toolchain with this for new components or additional hardware description methods. The generators take the intermediate artifacts to build and deploy the entire system. The toolchain uses and extends the open source solution from our previous work and thus also uses a grammar-based modeling approach based on attribute grammars. As opposed to other modeling approaches, grammars describe trees rather than models comprised of arbitrarily structured elements. In this work, we extend the approach to generate middleware-based interfaces to the generation of the entire system. One challenge is to have a concise but expressive description of the system. For this, there is a mechanism to describe the signals to connect one component to the other in a compact way, only specifying the ones to either include or exclude. This is of particular importance when the message specification is composed by a large number of signals. The previous slide showed the specification of a system which contains an HLS accelerator of an image processing application compliant with an image message type from the robot operating system. The figure here shows all the generated components. There are the two publisher and subscriber converters, and the generated wrapper for the accelerator. This message type contains fields which can change their size dynamically, so the total length of the message cannot be known at compile time. As the transmission of the message through the publisher converter cannot start unless the total number of bytes is known, a custom component for each message type to compute the length dynamically on each frame is also generated. Software implementations have access to large memory blocks, and the entire message is available constantly. This is not possible on hardware as data is streamed, which makes it necessary to have a mechanism to compute the total number of bytes in each frame as it can change dynamically. The viewer is encouraged for further details in the paper about the algorithm to generate the frame length component. The last challenge concerns the communication between PS where native ROS runs and the PL. The left figure shows the default scheduling scheme to receive new messages in ROS with a shared callback queue for all subscribers. Here, the callback queue needs to be read 3 times, retrieving B before A can be read, which may cause a message not to be longer usable for a given subscriber. The proposed modification is shown on the right, taking advantage of the use of individual callback queues for each incoming message. However, as this is to be streamed to the PL, there will be a race to get a hold of the DMA, and complementary schedulers on the PS and PL are needed. In this case, the algorithm is based on the least recently used one to avoid resource starvation. This means that each callback queue with available data will be able to transmit its content. On the PS, the scheduler decides which thread can stream data to the PL. On the PL, the scheduler is part of the manager to coordinate the transmission for subscribers and publishers from PL and to PS respectively. 4 different use cases were generated to fulfill the requirements and prove how the challenges were solved with our contributions. The first one addresses the challenge of obtaining all the information, explicit and implicit, from the system specification. The second one shows the benefits of FPGAs with respect to software solutions and the lack of overhead of our custom generated components. The third one is a complex system with different types of accelerators and middleware interfaces specifications. It aims to evaluate the proposed scheduler for a hybrid hardware-software architecture. The last one exemplifies how easy it is with our approach to generate interfaces as well as wrappers based on data type analysis for the large and complex middleware message specifications. The takeaway here is the little effort required to manually define the system specification for complex robotic systems with not many lines. Even though not all the artifacts would have to be manually written, the ratio between the lines of code of the system specification and all the intermediate artifacts exemplifies the little effort needed to deploy each use case with our approach. To conclude, this work presents a model-based approach to generate FPGA-based architectures for robotic applications. Our systematic approach circumvents the arduous process that involves designing complex architectures and the modification of hardware accelerators needed to incorporate them in existing solutions. For this, a toolchain which takes a concise and expressive system specification is introduced. It derives a holistic model of the desired system and generates all the needed components. Thank you for your attention.